In this lecture, we're going to look at a set of probabilistic models, especially focusing on those that we can use in unsupervised learning. We're going to start with probabilistic clustering, and then we're going to see two types of graphical models, which are ways of representing in this probabilistic context, of representing probabilistic relations between random variables. We're also going to look at these Markov processes and then hidden Markov models, which are a very used model approach to unsupervised learning with sequential data, both for time series, for example, or sequences like biological sequences, documents, and so on. I'm going to show lots of equations as usual, but note that you don't need to memorize the equations. It's important. The important part here is to understand the idea and this language of mathematical equations, which is dominant in this field. So let's start with probabilistic clustering. Suppose that we have a probabilities model for the distribution of examples in some data set. So we have some variable y that can be a class or a group from which an example comes from, and this x would be, as usual, the features that we have that we can consider to be a vector of numbers, so some coordinates in some feature space. And we know that the joint probability of these two, so a point at some position having come from some particular group, we can rewrite this as the conditional probability of the point having those coordinates if it comes from that group, multiplied by the marginal probability of coming from that particular group. So if we have this model, which has this joint probability distribution, as we saw before with classification, we could not only be able to do clustering of examples over this set of groups, because we could see the group which that had the highest joint probability, but we could also generate examples from that distribution, because since we have the joint probability distribution, we can, selecting some group, sample from that probability distribution of the coordinates of examples in that group. Now, the problem in clustering is that we don't know the groups to which the examples are assigned, not even in the training set. So this is different from what we had in classification, where the classes were part of what we could observe on the training set and then wanted to predict outside. But in clustering, these labels are created by the model. They are not present in the data. So we use this convention here. Let's call it z instead of y, because these are latent variables. They are hidden from our observation, and so they must be created in the algorithm, with the algorithm that is clustering the examples. We have these parameters that we are trying to fine-tune, and we are going to maximize the likelihood of our parameters. So basically, we want to maximize the joint probability distribution of the points that we have, our examples, being distributed with those coordinates and belonging to those particular groups, given that we have decided these particular values for the parameters. Now, we saw this in k-mean, so our first look at expectation maximization, which was still not really expectation maximization, but it gives us the right idea. And this is basically the problem that we have here when we are doing clustering. But now let's consider that the way we are clustering the examples is to assume that each cluster can be represented by a Gaussian distribution. And this is the probability of finding points from that cluster in some particular region. So if we consider in one dimension, for example, the blue cluster could be something like this, and so the points would be distributed around here. The green cluster could be this one, and we would have points distributed around here, and so on. And this is the expression for this Gaussian distribution. We need two parameters, the mean and the standard deviation, that determine the midpoint of the curve, so the place of the highest probability, and the width of this curve. So we have a scaling factor here so that everything integrates to 1, and then we have this expression for the curve. So basically, we can create a number of Gaussian distributions, each with its own parameters, and we can assign the points to the different distributions depending on their shape and the probability of coming from those distributions. We can, this way, create a mixture of these curves by adding fractions of the curves together, so that the sum of all of these curves is still an integral of 1, so that we can interpret this as probabilities. And this is the idea of a Gaussian mixture model, which mixes together, sums together a set of Gaussian curves with different parameters, in a way that the sum of all the curves has an integral of 1. So this is what we need for the Gaussian mixture model. For multivariate Gaussian distributions, that is, this example here is only for a single dimension, but if we have several dimensions, instead of having just one value for the standard deviation, we have this covariance matrix, which is a square matrix of the same, with the same number of rows and columns as the dimensions, and this is how we compute the spread here in different directions. So we are going to take the vector between each point and the mean, and then multiply that by the covariance matrix. And this basically determines the shape of the Gaussian curve in different directions, because it may not be spherical, it may be longer in some dimensions than others, and so on. So this is simply the expression for the Gaussian curve in n dimensions, where we need the parameters for the covariance matrix and the midpoint of the Gaussian distribution. And then we create a mixture of Gaussian curves by assigning to each of the curves, if we have k Gaussian distributions, each one will have its own value pi here, which is created such that the sum of all of these values adds up to 1, so that once we sum all of the contributions from all of these Gaussian distributions, we have a probability distribution. We have something that integrates to 1 and it's greater than 0 everywhere, and so on. So this is what we need for a Gaussian mixture model, a set of Gaussian curves, distributions in the dimensions that we are working in, and for each of these Gaussian distributions, one weighting factor, so that everything adds up to 1. So how can we now use this for clustering? We can start by creating a variable, let's call it Z, the hidden variable here, that can take values between values of 0 or 1 and indicates if a point belongs or not to one cluster. So for each point, for each value x, we are going to have these k z variables that indicate if the point x belongs to cluster k. And we're going to make them so that the sum of all of these k variables for point x adds up to 1, meaning that it must be 0 for all clusters except one cluster, which must be 1 where the point belongs to. And now we can look at the distribution of the positions of the points and the values of these z variables that indicate to which cluster each point belongs. So these are the latent variables that our clustering will assign to the points in order to attribute the points to different Gaussian curves. Now, the marginal probability of a point belonging to some cluster is the fraction of that Gaussian distribution in the mixture. So this means that without knowing where the point is at, without knowing the features of the point, we can consider the probability of the point belonging to a cluster to be simply the fraction of that particular cluster in the whole distribution. So a Gaussian distribution that contributes with a larger fraction will have a larger number of points. And the probability of a point being placed at some position, if it belongs to cluster K, is given by the distribution, by the Gaussian distribution of that particular cluster K. So we have the parameters for the Gaussian distribution K, and this is what allows us to compute what is the probability of a point being placed at any particular position. So basically we can rewrite these probabilities as a function of the Gaussian distributions that we have with their corresponding parameters. So the probability of a point being in some particular place is the weighted sum of the contributions of all the different Gaussian distributions, each one with its own weight and each one giving its own probability of the point being in that particular position. Okay, so now we can use Bayes rules and these equations and get the posterior probability that for this particular point xn, it was the Gaussian distribution k that produced that point. So that point is assigned to that Gaussian distribution k. Let's call this the gamma of this z variable, which is the probability that we have a value of 1 on the k z variable, that is the k cluster for point n. And we can do this by considering the probability, the marginal probability of any point belonging to cluster k, and multiply this by the conditional probability of a point having these particular coordinates if it belongs to cluster K. And if we take the fraction of this for the sum of all the different clusters, so adding this for all the K clusters, then we have the probability of the point having a point with these coordinates having come from cluster K. So we can do this using the Gaussian curves and adding for all the clusters and computing for this particular point with these coordinates. So this is let's call it a gamma so that we don't have to carry this expression for the other conditions. And now what we want to do is to adjust the parameters that we have for all our Gaussian distributions. So the coefficients of how much each Gaussian distribution is weighing on the mixture model, the mean points, the central points of each distribution, and the covariance matrices that give us the shape of these distributions. And we want to maximize the logarithm of this. So basically we want to maximize the logarithm of the probabilities of the points having those coordinates given the contribution of all of those Gaussian distributions. So skipping some parts here where we compute the derivative set to 0 and so on, basically what we have is when we set the derivative to 0, we have these expressions for computing the mean point. So basically the mean point of each Gaussian distribution k will be the weighted average of the coordinates of the points, but each point weighted by the probability that the point came from that particular distribution. So given the coordinates, this gamma here that we computed here is given the coordinates of the point, the probability that it belongs to cluster K. So this basically is telling us how much each point is weighting on the central point for cluster K, and we are averaging this by normalizing with the sum of all of these contributions. So all the probabilities of all the different points having come from cluster K. And this is the effective number of points in component K in this cluster, which is basically the sum of these fractional probabilities of the points having come from that cluster. So this allows us to compute the best point where to center each Gaussian distribution K, given the coordinates of the points that we have, that we can observe, and given the probabilities of each of those points having come from each of these Gaussian curves. We can do the same for the covariance matrix. So basically this is the same idea. We are computing the multiplication here of these vectors between the coordinates and the center of the distribution. Note that it's the vector and the vector transposed, so this will give us a square matrix with the covariance matrix when we add to all the points that belong to the cluster, but each one is weighted by the probability of that point belonging to the cluster. And to get the marginal probabilities of coming from any particular from each particular cluster, we can just consider the fraction of the effective number of points that we have in each cluster, which is the sum of all the probabilities of the points belonging to that cluster divided by the total number of points. So this gives us how much each Gaussian distribution is weighing on the whole mixture. Okay, so this allows us to get the maximum likelihood solution for the central points of all the Gaussian distributions, for the covariance matrices of all the Gaussian distributions, and for the weight of all the distributions. But the tricky part here is that we need this probability, the probability of a point belonging to one of these Gaussian distributions, in order to compute the best set of parameters. So to maximize the likelihood, we need the probabilities of the points belonging to the different Gaussian distributions. And we can only get these probabilities when we already have the Gaussian distributions with the parameters, because we need those to compute the probabilities. So this is where expectation maximization comes into play. First, we do the expectation part when we use these probabilities to create the likelihood function. So note here that our likelihood function is the probability of the probability of the data having those distributions being distributed in those coordinates given the parameters that we have. So once we write this function, we can now compute the set of parameters that maximize this expression. So in order to have this likelihood function, we need first to compute these probabilities, and so we need an initial guess for the parameters. And then we maximize the likelihood function, and we obtain new values for the parameters that are better than the previous one. So this would be the expectation step, where we use these expected values to create the likelihood function, and then the maximization step, where we compute the parameters that maximize the likelihood function. And now we step back and forth in these two steps until everything converges, or until we stop the iterations. So here are some graphical examples. Suppose that we have a set of points distributed in these clouds, and we use two Gaussian components. This is the result after the first pass, where we determine the central point and the standard deviation by maximizing that likelihood function. Now we recompute the likelihood function, because now we have different parameters, and we maximize it again, and we have this result after 2 passes, after 3 passes, and so on. So in this case, it's not a very good model, because we only have 2 Gaussian components, where clearly we have 3 clusters, but we can do the same thing with the 3 Gaussian components. So again, after the first pass, the second pass, the third pass, and as we iterate through these expectation and maximization steps, we keep improving the parameters that define the central point and the covariance matrix of our Gaussian distributions. So if you want to do this with scikit-learn, you have this Gaussian mixture class that you can import, and then you simply say the number of components. Typically, you can change some constraints on the covariance, because you can force the distributions to be spherical, to be elongated only along the axis, or any combination. So the fewer the constraints you have here, the larger the number of free parameters you have on the covariance matrix, but the greater also the ability to model different shapes of the clusters. Okay, so now let's look at graphical probabilistic models, which are ways of representing relations between random variables in graphs. And we're going to look at basically two different approaches. Bayesian networks use directed cyclic graphs to represent how the variables are related by indicating conditional probability relations. Markov random fields use undirected graphs to represent the dependencies in groups of variables, and also as a way of representing conditional independence between groups of variables. Then we're going to take a look at more specifically at dynamic Bayesian networks, which are basically Bayesian networks that represent some sequential transformations, and move on to hidden Markov models with this. But the fundamental ones are these two, Bayesian networks and Markov random fields. The idea of a Bayesian network is to create a graph that represents with the directional edges the conditional probabilities that relate different variables. So as you know, we can factorize a joint probability distribution into products of these marginal and conditional probabilities. So the joint probability distribution of these three variables is the same as the product of the conditional distribution of C given A and B, then the conditional distribution of B given A, and finally the distribution of A. We could do this in different ways, so we have different possible factorizations, but basically the joint distribution of A, B, and C could be represented with different conditional probabilities. But with a Bayesian network, we can use this to express something like causality, for example. So taking this example, we know that if someone turns on the sprinklers to water the grass, or if it rains, then the grass will be wet. So the probability of the grass being wet depends on whether or not the sprinklers were turned on and whether or not it rained. And this is indicated here by these arrows that indicate this conditional probability. On the other hand, we generally do not turn on the sprinklers if it rained, because that would just waste water. It would not be necessary. So the probability of turning on the sprinklers will depend on whether or not it rained. And rain is something that we do not control here. So rain, the probability of rain is just some variable here that is independent from the rest. So this way we could represent these kinds of relations between the different variables. What we need for a Bayesian network, this is the graph itself. It has these nodes that represent the random variables. The arcs have a direction that represent conditional dependency. So this means that C is conditionally dependent on B. And we can consider that the set of variables on which one variable is dependent is the parent, the set of parents of that variable. And also we can say that the variables that depend on some particular variable will be their offspring. If we have some value that is observed, so some variable that we can observe, and so the value is fixed, we can also represent it in the graph by using, for example, a shaded node. We can represent parameters as special nodes. Note that parameters are not really random variables. They are set by some process in our model. And so we can represent it as a special node like this. But in any way, the idea here is that using this model, we can specify the conditional relations between the different variables, and then we can easily compute the joint probability distribution as a function of these variables. Basically, the joint probability distribution for the whole set of variables is the product of all the conditional probability distributions of each node given its parent nodes. That is, all the nodes that have arrows pointing to this one. Taking this example from Bishop's book, you can find it on this page if you want to look at it in more detail. The probability distribution, the joint probability distribution of these 7 variables, using this set of conditional relations can be written as the product of the distributions of these variables x1, 2, and 3. These three, they have no parents, so they are here on their own. Then x4 is dependent on the values of x1, 2, and 3, because we have these arrows here. So x4 has this conditional probability based on the others, and so forth. x5, x6, x7, they all have their parents here on their conditional probabilities. And since this is an acyclic graph, we can do this iteratively if we have, for example, observations for determining the probability distributions and so on, and then compute the actual values. A different way of representing these relations between random variables is with Markov random fields, which are undirected graphs. So the difference here is that directed graphical models like Bayesian networks can be used to specify these conditional dependencies between two different variables, but then the separation in independent groups becomes a lot more complex to represent. Undirected graphs can represent this conditional independency between groups better, and I'm going to explain this a bit more. So basically we have an undirected graph where we have a set of random variables and the edges that link them together. Everything that all the variables that are non-adjacent will be independent, conditionally independent, if we fix everything that is in the path that joins them together. So basically these are these properties here, but we can see them visually more easily. Suppose that we observed the values of these variables here. So we know what the values of these are, and they are fixed now. This means that under this Markov random field, with this graph, the variables here in A and in B are now independent of each other, because since we are observing the values here, there is no information that can flow from one to the other. Basically, whatever value we have here, it doesn't matter for that one because this one is already fixed. Now, if this one was not fixed, then a value there could influence the value here, and the value here could influence the value here, so there would be a connection between them. But once we fix the values in the pathway, then these groups become independent. So this is what we mean when we talk about A being conditionally independent of B given C. That means that if we know the values of C, we block any information flow between A and B, and now we can consider them to be independent. So one consequence of this is that Markov random fields allow us to better represent this conditional independence of groups of variables, and also allow us to represent the joint probability distribution of all the variables looking at clicks, specifically at the maximal clicks, which is more practical. A click in a graph is a set of nodes that all have connections between themselves, so fully interconnected. A maximal click is a click that we cannot augment, we cannot add nodes and still remain a click. So, for example, here, the group formed by 1 and 2 would be a click because 1 and 2 are connected together, but it would not be a maximal click because we could still add 5 and obtain a larger click. 5, 1, 2 is a click because they are all connected to each other. For example, here 4, 5, 2, 3, this square is not a click because there are some connections missing between 4 and 2 and 3 and 5. So we could identify the maximal clicks here. In this case, it would be these groups. And now we can write the joint probability distribution as the sum function of each maximal click and then the product of that function. So as long as we have the right scaling factor here, so the scaling factor is simply the sum for all the points of these products here for the functions, then this will add up to 1 over all the possibilities, and we have a probability distribution. Now, the way we can choose this function and the parameters for the function and so on depends on what we want to express and what we how do we want to set the relations between the variables. Let's look at a simple example of how we can use this. This is in more detail in Bishop's book if you want to take a look, but the idea is to use a Markov random field to help denoise an image. We have this image where noise was added by changing the pixels from background to foreground. So we can imagine that we only have 2 colors per pixel, the background and the foreground. We have added noise by changing it at random, and now we can use a Markov random field to recover, at least remove most of the noise from the image. So the Markov random field here is, it has these variables which are observed. So these y variables are the values of the pixels that we are seeing here. And then we have these hidden variables which are the values, we can use them to represent the true values of the pixels, which we cannot really observe directly because we are only looking at the noisy data. But this is the noisy data, and these are the real values of the pixels. And this Markov random field, this graph, means that the true value of a pixel is related to the value that we observe on the noisy image, but it's also related to the values of its neighbors on the true image, because we can see that generally the pixels should be similar to their neighbors in many regions of the image. And now we can create this energy function. This is an analogous to the Boltzmann distributions in physics and so on. But basically, we are creating this function that expresses what we think would happen in the true image. We have a contribution for the relations between the hidden variables here in the neighborhood, so the neighboring pixels, and we have this beta factor here with the product of the values of the pixels. So the values here can be -1 or 1, depending on whether it's background or foreground, the color of the pixels. And so this means that if the values are different, this will be a negative value, and we are subtracting that from the energy function, so that we increase the energy if the values are different, because we have this minus sign here. If the values are the same, then the energy lowers in this function that we are writing here. We also do the same thing for the relation between the hidden values and the observed values. That is, the values we observe in the noisy image and the value we assume the true image should have. So we have a different parameter here, but it's also a negative sign. And now we can add a bias also for setting these pixels to 1, and with a weight that depends on what we think should be the proportion of pixels in the foreground color. So we can set these parameters, and now we can compute the parameters, and we can compute the values of the variables here, the hidden variables, that minimize this energy function. So once we minimize the energy function, we obtain this denoised version of the image, because we are trying to keep the same value on the hidden variable and the corresponding observed variable in the noisy image, but at the same time we are trying to keep the same values on neighboring pixels. So by managing the two things together in this energy function, we can remove most of the noise from the noisy image and recover a better image here. Okay, so let's review the difference between the Bayesian networks and Markov random fields. Both of them try to model how the variables are related and how they depend on each other, but Bayesian networks are directed as cyclical graphs which specify the conditional dependencies between pairs of variables. So there are some dependencies that we can represent in Bayesian networks that we cannot represent in Markov random fields. For example, that C depends on A, but A does not depend on C. This is something that we are saying here, but we cannot say this with the Markov random field where the edges are not directional. However, with Markov random fields, we can have cyclical dependencies, and we can have set cliques of variables that are all interdependent without having to specify in which direction this conditional dependence is. So we can include these and represent these relations differently, and they can be used for different applications. Another way of using these Bayesian networks could be to represent some process that occurs in a sequence. It may be over time, or it may be, for example, along a text document where you have different words in the sentences and then different sentences in the chain. So we can represent something that occurs in a sequence, and a simple process like that is a Markov process where the state at each instant depends only on the state before. There are many different examples of Markov processes. For example, in games, in board games, if you're playing Monopoly, then the probability of falling in some particular place depends only on the place where you were immediately before. It does not depend on what happened in previous turns. It only depends where you are now. So this is an example of a Markov process, and we can represent this in a Bayesian network like this. The state at step 2 depends only on the state on step 1, and the state on step 3 depends only on the state on step 2, and so on. So if we know the state on step 2, we can compute the distribution, the probabilities at step 3 without having to look at step 1, because it doesn't matter what happened here if we already know what the state is there. So this is the Markov process, and the joint probability of all of these different states is simply the probability of state 1 multiplied by the probabilities, the conditional probabilities of each state given the state before. So for all the following states, we just look at the conditional probabilities given the previous state. So let's use this and look at hidden Markov models, which are these dynamic Bayes networks where we have a Markov process in the hidden variables. These X states are not observed, but for each state we can also emit some observable variable at each step here. And basically what we have is a joint probability distribution of all the hidden states and all the observed states Y here. And this is computed by the probability of the first state when we start the Markov process, and then the probabilities of the states changing along the Markov process. This is the same that we saw before, because it's just this process here in the hidden states. But then we also have the emission probabilities depending on each particular state. So the probability of emitting a symbol at time t depends on what the state was at time t. And this is the hidden Markov model basically can represent something that we are observing in a sequence. It can be a temporal sequence, but it can be a different sequence, and represent this as a function of some state that we cannot observe directly. This has we can represent this differently if instead of representing this as a Bayes network unrolled over time, we can represent this simply as the changes of state. So now note that x1, x2, and x3 are not the time steps in this representation. They are the different possible states. And what we're saying here is that there is a probability of going from state 1 to state 2, from state 2 to state 3. At each state, there are some probabilities of emitting each possible symbol, and basically along the process we'll be jumping in these states, and at each state emitting a symbol. So basically, to describe these a hidden Markov model, we need these sets of parameters. We need to know the probabilities of transitioning from one state to the next at each step. So we need this matrix called A that has, it's a square matrix of n by n, where n is the number of possible hidden states. And this tells us what is the probability of being in state j at times t if we were at state I at times t minus 1. So this is the value that we have on the position ij of the matrix, of this A matrix. Note that even though this has n times n parameters, since these must be probabilities, they must add up to 1, so not all parameters are completely independent of each other. But still, we need this matrix so we have all the probabilities of transitioning from one state to the other. We also need these probabilities of emitting different symbols, different state, observable states, depending on the hidden state at each time. So we need this probability matrix of k times n that accounts for all the n possible states and the k possible emissions, symbols that we can emit. So here we have, again, the probability of emitting symbol y at times t, depending on the state at times t. And finally, we need these probabilities here at the start of the Markov process. So we need to know the probability of each state in the first step of the Markov process, and basically we need one value for each of the possible states. We have this vector, which for each state gives us the probability that at the first step, this is the state that we have. So what can we use hidden Markov models for? Basically, whenever we want to use some observed sequence to infer something that we cannot observe directly. For example, in voice recognition, we can observe frequencies, sound frequencies over time, varying over time, but we need to infer from that what was the word being said at each interval of time. So we can consider that the different words are the states, the hidden states in our hidden Markov model. The sound wave is what we can observe, measure in the microphone. And now we can have a trained hidden Markov model that gives us the most likely words for each sound wave that we are receiving. And this will depend not only on the sound wave itself, what we are observing, but also on what the previous word was, because these state transitions also have some probability. And this is a good thing for voice recognition, because usually in a sentence the words are related in sequence. This has also been used to recognize persons by the way they walk, for example, and it's not only for patterns in temporal data, but also patterns in any sequential data. For example, hidden Markov models are very used for dealing with, in bioinformatics, for clustering protein sequences, for annotating genome sequences, finding the genes and the different functional parts on the genome, and so on. So essentially, whenever you have observations of sequential data and you want to infer something that is not directly observed but may also be occurring in sequence, hidden Markov models tend to be useful for that kinds of problems. So what can we do with the hidden Markov model? One thing that we can do is try to predict the probability of some particular state after a sequence of observations. So this is called the belief state. The belief state that we have this particular, it's the probability of this particular state at times t, given what we have observed so far between the beginning until the current time t. This can be used, for example, if you have different Markov models to classify sequential data, for example, to classify different documents or different protein sequences and so on, and you want to measure the probability that one particular sequence you observed belongs to each of those hidden Markov models. You can compute the most likely model by looking at the maximum belief states after the end of the sequence for all of these hidden Markov models, and then pick the one with the largest probability. This is the one that is most likely to have generated that sequence. Now, this is hard to compute if you have to consider all the possible combinations of hidden states, because if you have n hidden states and t steps in your sequence, then you have n raised to the power of t combinations, and to go through all of these combinations would be prohibitive. But given that the emission of the observed value at times t only depends on the state at times t, and the state at times t only depends on the state at times t minus 1, we have this forward algorithm that allows us to compute the belief states much more efficiently. Basically, the belief state at the beginning of the sequence is the probability that we start with that particular state I. This is given by the value of pi for I, and then multiplied by the conditional probability of having that symbol in the first place in our sequence if we had state I. So we are putting together both the marginal probability of starting at that particular state and the probability of emitting that symbol that we observed in the first state. And now we can do this for all the subsequent type steps. So basically we have this recursion relation in which tells us that the probability of being at some particular state at times t is the product of the probability of emitting this symbol that we observed at times t if we are in this state, multiplied by this sum of the probabilities of each state that we can have, depending on whatever state we were at the previous time, at times t minus 1, and multiplied by the probability that we had that particular state. Because note that we are computing these belief states for all the possible states. So that means that at times t minus 1, we could have been in different states, but we had different probabilities for the different states at times t minus 1. So we can consider the transition between this state at times t minus 1 and the current state, multiplied by the probability that we were at this particular state on the previous step. And so we can move forwards here and compute the probabilities for all the possible hidden states along this sequence, and then look at the maximum one at the end. And this can we can use this, for example, for selecting which is the most likely hidden Markov model to have generated that sequence. And this is something that is used for clustering protein sequences, for example, in protein sequence databases. We can also try to compute the most likely sequence of hidden states given a sequence of observed variables, of observed states. And this is done by the Viterbi algorithm. I'm not going to detail it very much, but it's similar, the idea, it's similar to the forward algorithm. But what we're going to do is we're going to keep two matrices that have as many rows as the number of states and as many columns as the time steps that we have. And at each column, we are going to compute for each state the probability of the most likely previous state for getting there. And since we also keep the index of the most likely state for each of these cells in the matrix, we can then retrieve the most likely path by tracing back from the end of the matrix, the place with the highest probability, and looking always at the changes with the highest probability. And at each place of the matrix, we will have the probability of the most likely path so far for at each time step. So basically, with the Viterbi algorithm, we can use this dynamic programming approach to compute the most likely sequence of hidden states given the observed states. And this is very used for things like speech synthesis and even in wireless communication, for example, because you can observe the noisy data, a sequence of signals, but you need to infer what is the actual data that was sent. So Viterbi decoding can help with reducing the problems with noise in communication. It's also used in bioinformatics, in speech recognition, things like that. So these are not quite the same thing, although they are similar in the computations. Note that the forward algorithm is used basically to compute the probability of some final state given the sequence of observations. So you can use it, for example, to compute the likelihood that this sequence came from a particular hidden Markov model, whereas the Viterbi algorithm is telling you the most likely sequence of states, not just the probability of having that sequence of observations, but the actual hidden states that are most likely given those observations. Of course, all of these that we saw so far assumes that we know the parameters of the hidden Markov model. So we already have the hidden Markov model computed. We know all the parameters, all the probabilities of transitions, of emissions, and the initial probabilities. And so we can use these algorithms to compute these probabilities and the most likely sequences of hidden states. But we first start by training the model, so we need to find the best parameters. And again, this is by expectation maximization. The Baum-Welch algorithm is an example of expectation maximization, in this case applied to training hidden Markov models. We start with an initial guess for these parameters, so the matrix that gives us the probabilities of transitions between hidden states, the matrix that gives us the probability of emitting some observable symbols depending on the hidden state, and the vector with the initial probabilities for the first step in the Markov process that we have in the hidden states. And now we're going to start by computing these two sequences here. So these are called the forward pass, which is basically the forward algorithm that is going to compute the joint probability distribution of the state at times t and all the sequences so far. So this is, we can do this also recursively by starting with times 1. This is basically considering the emission probability for this first symbol at time 1 and the probability of the initial state being this particular state here. And then we're going to compute this forwards in time by considering the emission probability at times t, and then all the transition between times t minus 1 and times t, but considering all possible states at times t minus 1, weighted by the probability of having been in that state times t minus 1, considering the sequence of observations up to that point. So this is similar to the forward algorithm that we saw. We're also going to do the backward pass, which is looking ahead. So note that here we have the joint probability distribution of being in this particular state at times t and having observed all the sequence so far up to times t. And now we're going to consider the probability of having the sequence from the next step to the end, from times t plus 1 to the final time step, assuming that we are at this state at times t. So what is the probability that we're going to emit the next part of the sequences if we are in this particular state? And this we can do with the backward pass by starting at the end with this probability 1, because we no longer have, if we are at the final stage, we have no more sequence to emit, so everything is over. But now we can compute backwards, so each previous step, based on the emission on the following step, on the transition between the current step times t and times t plus 1, and the probability of emitting the rest of the sequence from then onwards. So for different states on the following step, t plus 1, we consider the probability of emitting the rest of the sequence. So this is, there is some analogy here between the two, you can see in the expressions, but basically this one is considering the probability of having a state at some time step and all of the sequence we observed so far, and this one is considering the probability of the next of the sequences from the next step to the end, if we assume that we are at this state. So now we can use these together to compute these probabilities here. So one is the probability of having the state I at times t, given all the observations that we have so far. So considering all the sequence of observable variables, and of course we need to assume some the parameters for the hidden Markov models. So if this is computed by the product of these alpha and beta for t, so basically the product of the probability of being at this state and having the sequence so far, and the probability of having the rest of the sequence being emitted if we start at this state at times t. So we multiply these two together, and we divide this by the sum that we get over all possible states at time t. So we have all of these alphas and beta computed for all the possible n states. So the fraction of this product over the sum for all the possible states gives us the probability of being at state I at times t, knowing what we know about the whole sequence of observations. We also need to compute the joint probability of being at state I at times t and at some state j on the next time step, t plus 1. So what we're doing here is we are considering the probability of being at times t and having all of the sequence so far, the transition to state j at times t plus 1, and then the probability of emitting the rest of the sequence after this step t plus 1, and the actual symbol that we emitted at t plus 1, the probability of emitting that symbol. And again, we normalize this for all the possible combinations of states at times t, states I at times t, and states j at times t plus 1. So these m and n are all the combinations at times t and times t plus 1. And the fraction of this for each particular ij is the joint probability of having this transition, so starting at times at state A at times t and then stepping to state j at times t plus 1. Okay, so now from this we can do the maximization step. Using this, we can write the likelihood function for the different parameters, and at the maximization step would be to compute the values for all our parameters that maximize this function. So basically the values pi, which are the probabilities of being in some particular state at the first step in the Markov process for the hidden states, is simply this gamma for t equals 1. So the probability of being at that particular state at the beginning, considering all the observations that we saw so far. This would be the best guess for this probability. The transitions between the two, the consecutive states, is just what we get here, the joint probability for being in I at state t and being in j at state t plus 1 for all the different states. And we normalize this by the marginal probability of being in those states for at times t. So basically, this way we can compute the best estimate for the probabilities of transitions by using the joint probabilities of being in the states in consecutive time steps, normalizing by the marginal probability of being in those states. And now we need also the emissions. So basically, we are looking here at the actual emitted sequences, emitted symbols at each particular state. So we know because we observe the y values here, so we can use the for each particular emission that we observe, we can consider the probabilities of being in each particular state and normalize that by the sum of these probabilities of the states given the complete sequence that we computed here. So basically we are computing here the frequencies with which we saw the symbols emitted by each state, weighted by the probability of being in that particular state. So this is basically the Baum-Welch algorithm, and we start with an initial guess of the parameters, and by computing these probabilities, joint probabilities of hidden state and the emissions so far, and the probability of the future emissions given the hidden state at each initial time, so at each time and the future emissions after that time, we can use this to compute these probabilities. The probability of being in some particular hidden state at each time given all the observed emissions, and the joint probability of having two consecutive hidden states at each time step given all the emissions. So this basically allows us to create the likelihood function by estimating these probabilities, and this likelihood function will depend on the parameters of the hidden Markov model. So to calculate this likelihood function, we need a first initial guess of the parameters. But now, once we have the likelihood function, we can maximize it to find a better estimate for the parameters, and we step backwards and forwards here until we reach convergence. Now, this may not give us the optimum value. It has all the problems that you have when you are adjusting models to the data. So if you have not enough data, it may overfit the data and so on, but it works in practice, and you can train the hidden Markov model in this way. So also hidden Markov models are generative models. Remember that we have the joint probability distribution. So basically we can now roll the dice and choose an initial step for the hidden Markov process in using those pi values, the initial probabilities for the different states. And then we can use those probability matrices to compute the transitions at each step and what is emitted. So you can use this to generate sequences, to generate speech, things like that. You can also use to classify, because if you have several hidden Markov models, each one trained with a different set of data, you can now use the forward algorithm and compute the maximum probability of some belief state after a sequence, and so you can select which hidden Markov model corresponds better to any sequence of observables that you have. And this allows us to recognize words, cluster protein sequences, things like that. Okay, so to sum up, we saw probabilistic clustering, where we saw a more detailed instance of expectation maximization. K-means is not quite expectation maximization, but it gives us the general idea. Gaussian mixture models actually uses expectation maximization because we are dealing with those probabilities. We saw briefly graphical models, Bayesian networks, and Markov random fields, and this notion of the Markov process. It's a random sequence of states where each state only depends on the previous state. And we use the Markov process as a process for the hidden states in a hidden Markov model, and from which are emitted observables that we have in our data. So we saw with the Welch algorithm how we can train the hidden Markov model with expectation maximization in order to compute all of those parameters, the transition probabilities, the emission probabilities, and the initial states, and also other algorithms like the forward algorithm and the Viterbi algorithm that allow us to compute things like the probability of having generated that particular sequence, or a sequence of hidden states that best corresponds or is most likely given a sequence of observables. If you want to read more about these, you have these sections in Bishop's book. They approach these subjects in more detail.